Hello and welcome you all to the 18th lecture of this NPTEL course, Electroweak Interactions in the Standard Model of Particle Physics. And in this lecture, we are going to carry on with this idea of electromagnetism that we started developing in the last lecture. And today we are going to talk about, what exactly are the polarization degrees of freedom and how exactly the relations between them and so on and so forth. But in order to do that, let us first briefly recapitulate what did we say in the last lecture. Okay. So, basically we started from the concept of Maxwell's equations, which we all know, which are like divergence of E is equal to rho, divergence B is equal to 0, curl of E is equal to minus del B del T, and curl of B is equal to J plus del E del T, and these were all written in the vacuum. And this leads to the concept of a 4 vector potential, which can be constructed in terms of a mu with phi and a sitting as its 0th and the last 3 components of the 4 vector potential. And interestingly, with this field a mu that we actually could define, we could define a field strength tensor which is like F mu nu defined as del mu a nu minus del nu a mu. And with this we could actually find a Lagrangian which is actually defined in terms of minus 1 by 4 f mu nu, and we could actually then do the Euler-Lagrange's equation, and with the Euler-Lagrange's equation like del L del A alpha del beta del L alpha del of del beta A alpha equal to 0, we could actually show that it satisfies, or it rather brings you back to the Maxwell's equation, which is like del beta F beta alpha equal to 0. Okay. So, this is therefore really a legitimate Lagrangian which can give rise to the equation of motion as the Maxwell's equation for sourceless field. And then we further could also, we did not do this calculation, but we stated that if you have a source term in the Lagrangian like minus 1 by 4 f mu nu minus j mu a nu, then you actually can get that equation like del mu f of mu nu is equal to j nu, which is a Maxwell's equation with the source term, right. And we then said briefly that there is also an interesting freedom in choosing these A fields, and that is basically given by the point that mu can go to mu prime, which is mu minus del mu chi, and if you write it in this way, then you can show that E and B definitions remain intact, and that also keeps the Lagrangian, which is like minus 1 by 4 f mu nu invariant. So, this is exactly where we actually gotten up to. Now, I would like to the question that what can be the choice of this chi, which is of course a function of the space time points x. So, what can be this choice? So, the answer is that there are several possibilities of doing that, and that is what is called the choice of a specific gauge. The one that we are going to adhere to is called Lorentz gauge. Now, this Lorentz transformation and this Lorentz gauge, these two are two different people. So, this is LORENZ are Lorentz transformation that had actually T. So, these are two different people and these are two different names. So, the Lorentz gauge is the gauge which actually helps you choosing a specific chi for this freedom that you are exercising for the electromagnetic Lagrangian and the electromagnetic field, which remains invariant under the transformation like mu going to mu prime, which is mu minus del mu chi. And this is also going to help us in deciding what exactly will be the choice of mu that we are going to choose. What is this Lorentz gauge condition? This condition says that del mu equal to 0. Now, this is basically fixing what can be the choice of chi that we can actually get from here. Now, this is not only the possible way of fixing what can your chi be. There are other possible choices like divergence of A. Simply you choose divergence of A equal to 0, that is what is called the Coulomb gauge. A3 is equal to 0 is what is called the axial gauge. A0 equal to 0 is called Weil gauge, and so on. So, but the point is, if del mu mu equal to 0, when you transform it to mu prime, because that keeps everything intact, so then del mu prime will also be equal to 0, right? And then you can say that mu prime, which is actually mu minus del mu chi, so therefore del mu of mu minus del mu chi equal to 0. And just because del mu itself is equal to 0, so you can say that del mu of del mu chi, which is box chi, that is equal to del mu that is equal to 0, is what is the mandate of the Lorentz gauge condition that we choose. Now, what happens to the equations of motion? Now, let us remind ourselves that the equation of motion for this Maxwell's fields are del mu f mu nu is equal to j nu. You remember, this is what we are writing with respect to the field strength tensor that we defined. Now, let us write it for this one. So, del mu f mu nu is del mu nu minus del nu mu is equal to j nu rather. So, you see that these indices are essentially repeated, mu are the dummy and repeated indices, nu is only the free index which appears on the right hand side of this equation, which should be the legitimate way of writing it. Now, take the del mu on both of these terms here. So, then that will give you del mu of nu and then del nu mu. So, del nu mu. Now, you can actually basically take the del nu on this side and have del mu. So, this is what we do in the next step, that we have del nu bringing out. So, the first term is del mu of nu, which is nothing but box of nu, right. Box operator is essentially, you know, del mu, right, and this term is del mu mu is equal to j mu. But from the Lorentz gauge condition, we actually have already assigned del mu mu equal to 0, right. If you bring it back, then what happens? Following the Lorentz gauge, basically this gives you an equation like box of nu is equal to j nu, right. So, this Lorentz gauge basically tells you that your nu photon field or whatever that you want to say, that electromagnetic field, box of nu must be equal to j nu. Now, suppose you do not have a source term, like you treat j nu is equal to 0, then what happens to this equation? This equation basically says that box of mu, you know, you can write, you know, a mu or nu, just the point is that you have to conserve the indices on the both sides. So, box of mu, that will be essentially equal to 0. So, therefore, what you actually see here is that this actually solves a differential equation del mu mu, I mean nu is equal to 0. This basically says that it is a plane wave solution that we can actually associate with the photon field also, right. I mean, just because it is a box of mu is equal to 0, the way that we could say that phi, which solves box plus m square, phi is equal to 0, has a plane wave like solution. So is the case for photon. But now what you can say, that I can assign, you know, the vectorial quantity, the vectorial aspect. You know, mu is a special field, it is not a scalar field, it is not the fermionic field, rather it has a field which has a Lorentz index sitting here like mu, and you can say, okay, I can actually dump its vector like criteria into a quantity called epsilon mu q, and then I you know, append to that the plane wave solution, which will be something like e to the power minus I q dot x, say for example. Okay. So, this e to the power minus I q dot x takes into account that it is a plane wave solution, or it is a plane wave like a thing, and the fact that mu is a vector field, it is a vector field which carries a Lorentz index by itself, is actually dumped on this quantity of a epsilon mu q, and this is what is referred as the polarization states. So, the point is that the mu field, which is the electromagnetic field or the photon field, whatever that you want to say, it is a vector field, and its credentials are now embedded into this polarization vector or polarization states, which is defined in terms of epsilon mu q, otherwise it satisfies a plane wave solution. Now, you remember the case when we actually solved for the fermion for the Dirac fields. This was something like similar, that we saw that the Dirac fields actually need to have a special property, that this must be spinors. This can be, should be 4 component objects, and we plus the fact that it is like, it will be a plane wave solution for satisfying Dirac equation. So, then we said that okay, all right, we can dump that spinorial aspect of the Dirac spinors into those u and v spinors for particle and antiparticle with this phase factor coming in terms of e to the power I q x, attached to that one. So, similarly here that mu is a vector field which has this, the credential that of being vector field is assigned to the polarization states. Now, the point is that if I now take this test solution, put it back into the main equation, which actually it satisfies, having assumed that the source term is equal to 0, that is essentially box of mu is equal to 0, right, or so to say you have to write it like box of epsilon mu q into e to the power minus I q x equal to 0. Now, this box operator, because epsilon mu has a dependence on the q vector. So, the box operator will basically operate on this phase space part, and this is what it going to be do. This is going to bring minus q square here into epsilon mu q into e to the power minus I q x equal to 0. Now, wait and tell me that what exactly this quantity tells you. See, certainly I cannot say epsilon mu q e to the power minus I q x equal to 0. That will basically say that the field itself is a 0, which has no meaning. It basically then says that this q square, this must be equal to 0. Now, what is this q square? I mean, how exactly, q is basically the 4 vector assigned to 4 momentum vector assigned to this photon field, right. And so, in general what happens, that what is this 4 momentum square? This q is essentially, you can say this is E comma P, right. So, what will be q square? Q square is q mu, and so if you do this multiplication, this is nothing but E square minus P vector square. Why E square minus P square? As I said, that this q covariant mu is essentially G mu nu, the metric tensor, into the q contravariant mu, and just because this G mu nu has like 1 minus 1 minus 1 minus 1. So, when you bring it to the covariant level, it actually picks up a negative sign. So, if q mu is E comma P, then q mu is essentially E minus P, and that is why q square is E square minus P square. Now, wait, E square is equal to P square plus m square for any field, right. So, therefore, q square will always be equal to m square, where m characterizes the mass of the particle. So, this is what we say, that q square is equal to m square is always the case for any particle. Now, here if you say that q square equal to 0, that basically tells you that the particle that you are actually describing here must have mass equal to 0. And so, this is essentially describing a massless photon. So, the point is as follows, that whenever you have an equation of this particular kind, like box of mu equal to 0, this is a wave equation for a massless vector boson. Now, there is another interesting point to this choice of the Lorentz gauge, which basically says that not all the components. So, what we did, that we wrote this interesting equation. We said that we can write this mu in terms of epsilon mu q with e to the power minus I q x. So, this is the relation that we actually have come up with, and then we said that this epsilon mu q is going to describe the polarization associated with the photon. So, this is what we have to resort to. Now, the question is, let us put this solution of a mu in the Lorentz gauge condition. Lorentz gauge condition kya tha? This was like del mu a mu equal to 0, right. So, this is the Lorentz gauge condition. So, let us put that. So, del mu of epsilon mu q e to the power minus q I q x, once again del mu will act basically on the e to the power minus I q x. So, I can bring the epsilon mu q outside, and del mu of e to the power minus I q x kya dega? This will give you q mu into e to the power minus I q x with a factor of minus I sitting out, and this is equal to 0. So, therefore, what you have to have that this is equal to 0. Now, if this quantity is equal to 0, I cannot say e to the power minus I q x equal to 0. That will be once again a trivial solution to have the field equal to 0. It makes no sense. So, this basically tells you that this epsilon mu q dot q mu, this must be equal to 0. So, it basically says that not all the components of the polarization vector are actually independent. If you resort to this Lorentz gauge condition, which is del mu a mu equal to 0, then basically this restricts the choice of your polarization vectors. Okay? So, not all only you have how many epsilon mu? You have epsilon 0, epsilon 1, epsilon 2, epsilon 3, right. So, now if you have a constraining condition like epsilon mu q mu equal to 0, that means there will be 3 independent components of epsilon mu that you can actually choose to describe the vector boson. So, this is an interesting point. And you can actually further impose some gauge conditions on the gauge transformations. How exactly you do that? Let us go back to this idea that what you are saying, that you have actually gauge freedom to write the a mu's to in the form of a mu prime, which is actually a mu minus del mu chi, right. And you say that the Lorentz gauge condition basically implies that del mu a mu prime actually is equal to 0. And this basically tells you that del mu a mu is equal to box of chi, and that is equal to 0. So, this basically tells you that the chi that you are actually choosing, which is giving you a freedom of choosing a mu, that also satisfies this plane wave equation, like box of chi is equal to 0. Now, what will be the solution? Now, this chi is a scalar field, or rather a scalar quantity. Scalar field, it's better to say, because I am assuming a mu to be a field itself. So, therefore, box of chi equal to 0, what kind of solution it can give? You can say that this is simply chi is equal to e to the power minus I q dot x or something like that, right. I will say that yes, you are absolutely right, but what I am going to do, that I am going to dress it up a little, and I say that the solution can be written as chi is equal to minus of I a into e to the power minus I q x. Okay? Now, if I do that, what will be box of chi? Box of chi will be, as you can see, that this will be q square into minus I a e to the power minus I q x equal to 0, which leads to the condition that q square equal to 0, and that is once again confirming that you are talking about something which is massless. You are talking about the massless photon. Okay? Now, let us come back. What happens if I put this explicit solution that chi is equal to minus I a e to the power minus I q x into the definition that a mu goes to a mu prime, which is a mu minus del mu chi. So, therefore, a mu was epsilon mu q into e to the power minus I q x. Chi was chosen as minus I a e to the power minus I q x, and so this will be I a del mu of e to the power minus I q x, which will give you something like epsilon mu plus a q mu into e to the power minus I q x. So, this is exactly what the form of epsilon mu prime becomes. So, if I translate this whole mathematical exercise in the physical world, it basically means that if you do a transformation of the epsilon mu to epsilon mu plus a q mu, then nothing will change. No physical quantities will be changing. So, therefore, it basically means that not only the fact that first of all you said that not all the polarization vectors are independent, epsilon mu q mu equal to 0 basically tells you that there are only 3 independent degrees of polarization. Now, for the massless case in specific, the fact that when you replace this epsilon mu by epsilon mu plus a q mu, you can keep everything intact, it actually restricts the choice of your polarization vectors further. Now, how? You can say that I can choose A in such a way that I make the time-like component of this epsilon mu vanish, or so to say I can choose epsilon 0 equal to 0, and this is what is referred as the Coulomb gauge condition. Okay? Let me explain you once more that you can have a freedom of choosing your a mu to a mu minus del mu chi. That was actually inherent in the definition of E and B or phi or whatever that you want to say. So, this will keep your definitions of E and B intact and the Lagrangian invariant. Then we further say that we can choose a specific gauge, and that will let us see how actually that fixes the choice of chi and so on, and we chose del mu a mu equal to 0, which was the Lorentz gauge. And in that gauge we actually found out that this is a consistent choice first of all, because this gives you q square equal to 0, which describes the massless photon, and at the same time this actually gives you a condition like epsilon mu, I mean you have a condition like box of a mu equal to 0, which is the equation of motion for a mu, so to say, and for the sourceless cases, and then you confirm that a mu must be chosen something like epsilon mu q into e to the power minus I q x, where epsilon mu q is the polarization vectors. Now, you say that what is the condition that I impose on the polarization vector from the Lorentz gauge condition, and you say that okay, this is simply coming from the fact that if you take del mu m mu equal to 0, then this is actually del mu epsilon mu is equal to 0, or epsilon mu q mu equal to 0, which says that you can only have 3 independent degrees of polarization for the photon field. Then you say that okay, all right, now if you choose what kind of chi that you can choose, then chi also seems to satisfy this equation like box of chi equal to 0, and you then say that okay, I can choose the form of chi in the form of minus I a e to the power minus I q x, and then basically you see that a mu prime can be written in terms of epsilon mu plus a q mu. And then basically you say that okay, if my Lagrangian, if my electric field, magnetic field, everything remains invariant under this transformation of a mu going to a mu minus del mu chi, that can be basically said in terms of its polarization vectors by saying if I write my epsilon mu as epsilon mu plus a q mu, then also it means the same thing. You know, this is the same freedom that we are talking about. Then you say okay, I can choose my A in such a way that I can actually choose one of these polarization degrees of freedom to be equal to 0, which is the time-like component is most of the cases. Then you say that you know epsilon 0 equal to 0 is another possibility that you hit upon, and that is what is called the Coulomb gauge. So, therefore, so to say, to summarize, that epsilon mu q mu equal to 0 basically gives you 3 polarization degrees of freedom, right? And further you see that the freedom of choosing epsilon mu going to epsilon mu plus a q mu, keeping everything invariant, and you can choose A so that you can make the 0th component of the polarization vector vanish, epsilon 0 equal to 0. So, that gives you basically that basically says that this is epsilon dot q is equal to 0 with epsilon 0 equal to 0. This basically says that the photon has only the polarization of photon is only transverse to the direction of its motion, and it has only 2 independent polarization states. So, this is what we actually come to, that this epsilon dot q is equal to 0 with epsilon 0 equal to 0, which is a result of the Coulomb gauge, which says that which utilizes this freedom that epsilon mu can go to epsilon mu plus a q mu. Okay. And you can actually, if you choose q is equal to E 0 0 p z, then you can say, okay, I can choose epsilon mu 1 degrees of freedom like 0 1 0 0, and the other one along y direction, and this is 0 0 1 0. However, once again, these choices of polarization that I just talked about is not unique. This is the case of what you call a plane polarized wave. You can actually have a circularly polarized wave, and that is something that you can exploit and see what are the circular the polarization vector for circularly polarized waves, but which still satisfies this condition that epsilon dot q equal to 0 with epsilon 0 equal to 0. Okay. So, this is where we come to, and then there is a very important relation which we will do in the tutorial exercise, which actually shows that the sum of the polarization states for the photon actually satisfies a condition like sum of lambda epsilon star lambda epsilon star mu lambda epsilon nu lambda is equal to minus g mu nu. Now, the part which we did not discuss here is the case what happens to massive vector boson. We have been talking about the massless vector boson, and we said that the we had everything very nicely, like minus f mu nu was the Lagrangian from which we got the equations of motion and blah blah blah, and we conferred that it is actually describing a massless photon. Now, suppose in some virtual world, or rather we are talking about some gauge bosons which are not massless, we are not talking about photon, we are talking about something else, but which has a similar kind of procedure, but that is a massive. How do I do that? So, then you say, okay, I can actually do that exercise by writing a Lagrangian. The kinetic piece, there is no change, it is minus 1 by 4 f mu nu, and but now I have to choose an explicit mass term, right. So, I can say that I can do it like saying minus m square b mu. Okay. So, this is the Lagrangian where I explicitly borrow a mass term, and then we can show that the equation of motion. Now, if you write the equation of motion, then this equation of motion turns to be not box of mu equal to 0, but rather box plus m square b mu is equal to 0, and this is what is called the Proca equation. Okay. So, this is something that you can derive, okay, for the massive vector boson field. Okay. And for the massive case, there is a third polarization degrees of freedom, which is often called the longitudinal degrees of freedom basically. And so, for the massless photon, you have two only independent degrees of polarization, because you could exploit that freedom of epsilon going to epsilon mu plus a q mu, which you cannot for the massive one, and you have a third polarization, and that is actually what is called the longitudinal polarization degrees of freedom. And for massive vector bosons, essentially you have a little change in the polarization sums, and this goes by this relation that epsilon mu lambda star epsilon nu lambda is equal to minus g mu nu plus p mu by m square. And the fact that mu basically has 3 independent polarization degrees of freedom, it confers that it describes a spin 1 boson or a vector boson with 2s plus 1 is equal to 3, which pertains to s equal to 1, right. So, this is the story about the photons and possibly a massive vector boson, which we are going to see in the real world in very soon. Okay, so with this I think I am going to stop here, and this completes the description of the electromagnetism and the possible way that we can write the Lagrangian and the possible way that we can exploit its polarization degrees of freedom and so on, and we will have some tutorial exercises on it also. And we are going to take up a new topic in the next lecture, and that is going to be a great fun. Okay, so stay tuned, and we will see you soon. Thank you very much.